Welcome to Space News from the Electric Universe, brought to you by the Thunderbolts Project at thunderbolts.info. In part 1 of this presentation, Thunderbolts colleague Peter Mungo Jupp began a provocative reassessment of the standard geological and anthropological timetables on planet Earth. We have proposed a radically alternative history for planet Earth, and indeed our entire solar system. In relatively recent times, there was a chaotic period in the inner solar system when planets approached one another close enough to exchange electromagnetic energy, taking the form of interplanetary lightning. One of these planets was Earth, whose close encounter with Venus, the Great Comet, was recorded in ancient texts around the world. In this scenario, in an era of prehistory, the Earth was bombarded with tremendous electromagnetic radiation. What effects did this have on our planet and its living organisms?
Most geologists and biologists work from a uniformitarian viewpoint, i.e. that's only small incremental changes in the last thousands of years. One, though, has only to read Claude Schaefer's works, the archaeologist in the Middle East, to realise that many violent perturbations have occurred within the last few thousand years. We're talking roughly no more than 8,000 years. And if one is to believe historical and many of the myths, as argued by Rens van der Sleij, then continent-encompassing floods, earthquakes, volcanoes, and massive electrical phenomena must have played a huge part in altering the carbon-14 isotopes concentration in living species. Also, dead carbon-13 from underground sources in huge volcanic eruptions must also falsify carbon-14 ratios, the concept of dead carbon contamination. Now, before we go on to the atomic clock mitochondrial DNA theory, let's just touch on one of the last archaeological modern science dating technologies: electric spin resonance, uranium thorium, thermoluminescence, and optical stimulated resonance. How accurate are these other methodologies used in establishing chronology? Electric spin resonance and uranium thorium series dating methods are secondary in the sense that they rely on measurements of isotopes and others not originally present in the living body, and the modelling of process taking place after burial. For instance, thermoluminescence and optically stimulated luminescence dating methods are applied to quartz grains in sediments containing skeletal remains, but not directly on the bones. Again, these must be subject to interpretation of the environment at the time of inception. Bryant notes that he found thermoluminescent dating highly inaccurate, with echoes of the Jimima affair, which we'll go into. When dating marine deposits, the laboratory result was 20,000 years BP before present. He maintains this cannot be accurate, for at the time the shoreline was well out to sea. He also remarks that this technique cannot be considered accurate if the event that initially triggered the zeroing of the quartz particles occur at night. It's light dependent. In this case, it will not start the clock ticking. He also notes serious age reversal effects with carbon dating. We have not always lived in an uniformitarian universe, and what happens today may have been, and most probably was, drastically different to our own relatively geological calm world. These methods too can be subject to gross error without knowing the physical, historical, geological history of the site. Cataclysmic events have often shaped the Earth in only the last few thousand years. Our reliance on scientific dating demands caution. I touched on the Jimima affair, which first declared a site as possibly 170,000 years before present using luminescence dating, but it was eventually found to be only 3,000 years old. Optical luminescence methods are highly subject to contamination, with Bowler from Melbourne University noting in his last studies of Lake Mungo that one lower level came up at a later date than the higher one. Impossible. He declared this was contamination, but there are serious flaws for this method, especially when water has at some stage washed through an area. In addition, it assumes zero crystal attachment when initially exposed to sunlight at its foundation. It depends on how it was formed, and this is hard to assume when the geologist was not there at its inception. Similarly, electron spin and uranium-thorium series methodologies make many assumptions gleaned from our uniformitarian present-day world and make no speculation on conditions evident in the Ice Age where unknown factors were probably at work. For instance, note the discrepancy between Bowler and Thorne's work at Lake Mungo. One came to 40,000 years before present, the other 60,000, a 20,000 year discrepancy. Carbon dating, if it's not standardised with dendrography, which only goes to 8,000 years, cannot be accurate. Remember, we're not doubting the accuracy of mass spectrometry used, only its universal application without time calibration controls. And finally, we move on to the atomic clock mitochondrial DNA phylogenetic theory. Aha! Is in fact mitochondrial DNA the atomic clock genetic scientists claim it to be? Eukaryote cells, that's mammal and other living cells, contain mitochondria within the plasma of the cell but outside its nucleus. Amongst other functions, they are an energy factory driving the cells. Curiously, they most closely resemble the bacteria Rickettsia and have many similar properties. What has become of great interest is the mitochondria's ability to transport, that's with exceptions, the female line to the next generation. The quality that excites interest is that a certain portion of the genetic chain of the mitochondrial DNA is subject to mutation in what is believed to be a constant rate within any species. Thus, analysis of past generations should reveal the number of generations noted at humans for 20 years per generation, and thus act as an atomic clock to peg the age of the specimen. Recently, an attempt was made to estimate the age of the human race using mitochondrial DNA. This material is inherited always from mother to children only, and there are exceptions, but that's a distraction. By measuring the difference in mitochondrial DNA among many individuals, the age of the common maternal ancestor of humanity was estimated at about 200,000 years. Is this true? A problem is that rates of mutation are not known by direct measurement and are often computed based on assumed evolutionary timescales. Note that, assumed evolutionary timescales. As we have seen in the previous work above, all these age estimates could be greatly in error. In fact, many different rates of mutation are quoted by different biologists. It shouldn't be very hard explicitly to measure the rate of mutation of mitochondrial DNA to get a better estimate on this age. From royal lineages, for example, one could find two individuals whose most recent common maternal ancestor was, say, 1,000 years ago. One could then measure the differences of the mitochondrial DNA of these individuals to find its mutation rate. This scheme is attractive because it does not depend on radiometric dating or other assumptions about evolution or mutation rates. It is possible that in 1,000 years there would be too little difference to measure. At least this would give us some useful information. Now, along this line, Parsons, one of these researchers, has recently done some work to measure explicitly the rate of substitution in the mitochondrial DNA control region. That's a narrow region where a lot of mutation occurs. And I'll read his summary. The rate and pattern of sequence substitutions in the mitochondrial DNA control region is of central importance to studies of human evolution and to forensic identity. Here we report a direct measurement of the intergenerational substitution rate in the human CR. Now, this is a way we can actually find the age. He compared these to what they call phylogenetic analyses that claim the use of mitochondrial DNA to ascertain the age of let's say, a particular Neanderthal, for instance. He found the observed substitution rate reported were very high compared to rates inferred from evolutionary studies, so using so-called mitochondrial DNA, in fact 20 times higher. Using our empirical rate to calibrate the mitochondrial DNA molecular clock would result in an age of this mitochondrial DNA of only 6,500 years, clearly incompatible with the age of modern humans as estimated by evolutionary studies. It remains implausible to explain what known geographic distribution of mitochondrial DNA sequence variation by human migration that occurred only in the last 6,500 years. In fact, the evolutionary molecular clock, as measured by mitochondrial DNA, has a long and troubled history. Hampered by a lack of empirically measured mutation rates, the evolutionary molecular clock researchers have historically assumed mutation rates by dividing two species' genetic differences by their evolutionary time of divergence, e.g. human-chimpanzee divergence, since the latter was inferred from the evolutionary age assignments in the fossil record, which is basically not very well understood. The evolutionary molecular clock amounted to a circle of evolutionary assumptions and never an independent test of a species' time of origin. The advent of modern molecular genetics has resulted in an increasing number of publications in which mutation rates in various species and in various genetic compartments have been empirically determined, independent of the evolutionary age assignments in the so-called fossil record. Using the mitochondrial mutation rates, predictions can now be made on how much mitochondrial DNA diversity should result after a specific number of years have elapsed. These studies represent an important and significant step forward in our understanding of the origin of human mitochondrial DNA differences. Though the mutation rate was measured only in European individuals, predictions with this mutation rate on the 6,000-year timescale captured the mitochondrial DNA diversity in all non-African people groups, including the major Eurasian groups and representatives of the native peoples of the Americas.